Hello everyone, welcome to Tech of the Day. Today we are going to talk about is create containerized solutions, Kubernetes. In this module, we will cover Azure Kubernetes Service, deploy an AKS cluster, publish a container image to Azure Container Registry, create and run container images in Azure Container Instances, and some hands-on Azure Container. So let's get started. This is covered in both AZ-203 and AZ-204. Let's go. Already we talked about topics. Lesson 1, Azure Kubernetes Services. What is Azure Kubernetes Services? In this lesson, we will cover Kubernetes, Azure Kubernetes Services, access and identity, security, networking, storage, and scaling of Kubernetes. Kubernetes is a powerful open source system initially developed by Google for managing containerized applications in clustered environment. It aims to provide better ways of managing related distributed components and services across varied infrastructure. So Kubernetes manages container-based applications along with networking and storage requirements focused on application workloads instead of infrastructure components, makes it easier to orchestrate large solutions using a variety of containers, application containers, storage containers, middleware containers, even more. Applications are described declaratively and they use YAML files to describe the application. Kubernetes and as applications grow to span multiple containers deployed across multiple servers, operating them becomes more complex. To manage this complexity, Kubernetes provides an open source API that controls how and where those containers will run. Kubernetes simply orchestrates clusters of virtual machines and schedules containers to run on those virtual machines based on their available compute resources and the resource requirement of um, the resource and those pods scale to your desired state. Kubernetes also automatically manages services, service discovery, incorporates load balancing, tracks resource allocation, and scales based on compute utilization. And it checks the health of individual resource and enables app to self-heal by automatically restarting or replicating containers. So just for an example, cluster architecture of Kubernetes. A Kubernetes cluster is divided into two components. Cluster master nodes provide the core Kubernetes services and orchestration of application workloads, and nodes run your application workload. Cluster master, when you create an Azure Kubernetes service AKS cluster, a cluster master is automatically created and configured. This cluster master is provided as managed Azure resource abstracted from the user, and it contains the controller manager that runs vendor specific logic for AKS. There is no cost for cluster master, only the nodes that are part of AKS cluster. Additionally, Azure manages the etcd database. In Kubernetes, etcd is used to store the state and the configuration of Kubernetes clusters. Node and node pools to run your application and supporting services. You need a Kubernetes node. An AKS cluster has one or more nodes, which is an Azure virtual machine that runs the Kubernetes node component, kubeproxy or kubelet, which is called, and the container runtime for that node. So Kubernetes nodes, each individual node is an Azure virtual machine. Kubelet is the Kubernetes agent that processes the orchestration requests from the cluster master and scheduling of running the requested containers. Virtual networking is handled by kubeproxy. So virtual networking is handled by the kubeproxy on each node. The proxy routes network traffic and manages IP addressing for services and pods. The container runtime is component that allows containerized applications to run and interact with additional resources such as virtual network and storage. In AKS, Docker is used as container runtime. Kubernetes terminology. So we have different terminologies: nodes, pools, pods, deployments, and manifestation. Nodes: an AKS cluster has one or more nodes, which is an Azure virtual machine that runs Kubernetes node components and container runtime. In AKS, the VM image for the nodes in your cluster is currently based on Ubuntu Linux. When you create AKS cluster or scale up the number of nodes, the Azure platform creates the requested number of VM and configures them. There is no manual configuration for you to perform. Node pools. Nodes of the same configuration are grouped together into node pool. A Kubernetes cluster contains one or more node pools. The initial number of nodes and size are defined when you create an AKS cluster, which creates a default node pool. This default node pool in AKS contains the underlying VM that runs your agent nodes. So pool is simply grouping of nodes with identical configuration. Pods. Kubernetes uses pods to run an instance of your application. A pod represents a single instance of your application. Pod typically have a 1 by 1 mapping with a container, although there are advanced scenarios where a pod may contain multiple containers. These multi-container pods are scheduled together on same node and allow containers to share related resources. So pods are single instance of an application. It's possible for a pod to contain multiple containers within the same node. A pod is a logical resource, but the containers are where the application workloads run. Pods are typically ephemeral, disposable resources, and individually scheduled pods miss some of the high availability and redundancy features that Kubernetes provides. Instead, pods are usually deployed and managed by Kubernetes controller such as deployment controller. Manifests: a YAML file for describing a deployment. And deployments: a deployment represents one or more identical pods managed by Kubernetes deployment controller. A deployment defines the number of replicas pods to create, and the Kubernetes scheduler ensures that if pods or nodes encounter problems, additional pods are scheduled on healthy nodes. You can update deployments to change the configuration of pods, container, image used, or attached storage. The deployment controller drains and terminates a given number of replicas. Create replicas from a new deployment definition and continues the process until the replicas in the deployment are updated. To understand more about Kubernetes terminology and Kubernetes, I would suggest you to watch a video from Microsoft, which is called Fifi. Fifi. Microsoft created a video with cartoon animation, and it is really interesting to watch it. It's 2 3 minutes video, I guess. You can search it online, Fifi Kubernetes Services, and you will see that on top. AKS, Azure Kubernetes Service. Azure Kubernetes Service provides a managed Kubernetes service that reduces the complexity for deployment and core management tasks, including coordinating upgrades. The AKS cluster masters are managed by Azure platform, and you only pay for AKS nodes that run your applications. AKS is built on top of the open source Azure Container Service Engine (ACS) engine. Simple management of cluster of VMs by using Kubernetes. So removes infrastructure complications and planning, no cluster charges, just use resources. Secure, reliable, highly scalable, supports node auto-scaling to meet resource utilization, supports in-place upgrade of clusters to the latest version of Kubernetes, direct integration with containers registry for Docker images, Azure Virtual Network integration for isolated network traffic. So AKS, I hope it's clear. Now we come to package management with Helm. Helm charts are a package that makes it easier to manage applications. Helm packages contains Kubernetes YAML manifest, packaged version of application code, and it can be stored locally or in a remote repository. A common approach to managing applications in Kubernetes is to use Helm. You can build and use existing public Helm charts that contain a packaged version of application code and Kubernetes YAML manifest to deploy resources. These Helm charts can be stored locally or remote repository, as I said, such as an container registry Helm chart repo. To use Helm server component called Tyler is installed in your Kubernetes cluster. The Tyler manages the installation of charts within the cluster. The Helm client itself is installed locally on your computer, or it can be used within Azure Cloud Shell. You can search for or create Helm charts with the client and then install them in your Kubernetes cluster. So Tyler deploy resources and services into the pod. Namespaces. So logical grouping of resources such as pods and deployments used to divide a cluster and restrict access. Kubernetes include built-in namespace defaults like default, kube system, kube public. So if you see here, kube system namespace contains kube DNS, kube proxy, kube dashboard, and engineering namespace can be whatever you want, block service, which is representing a pod. engineering uses. So Kubernetes resources such as pods and deployments are logically grouped into a namespace. These groupings provide a way to logically divide an AKS cluster and restrict access to create, view, or manage resources. You can create namespace to separate business groups. For example, users can only interact with resources within their assigned namespace. When you create an AKS cluster, the following built-in namespaces are available. So as I said, default, kube system, and public. Default, the namespace is where pods and deployments are created by default when none is provided. In smaller environments, you can deploy applications directly into the default namespace without creating additional logic separations. When you interact with the Kubernetes API, such as with Kube, Kube, Kubectl, so it is called kubectl, gets get pods. The default namespace is used when none is specified, and then there is kube system. The namespace is where core resources exist, such as network features like DNS and proxy. So as I said, kube DNS, kube proxy, and kube dashboard. You typically don't deploy your own applications into this namespace. And then there is kube public. This namespace is typically not used, but can be used for resources to be visible across the whole cluster and can be viewed by any users. So any namespace, any any resource, any resource stored in kube public can be accessed by not only you but other users in the same cluster. Of course, you can create any namespace you wish for your own services. So I hope it's clear. Next is access and identity. Service accounts, user accounts. There are two types of accounts. Service accounts managed by Kubernetes API. Credentials are stored as Kubernetes secret. User accounts, low friction way to authenticate for human administrators or developers. Must use an external identity solutions integrated into Kubernetes. For AKS, you can use Azure Active Directory. So let's say your application you are accessing and you are manually logging into some application, then you can use you can use Azure Active Directory to log in. And if any of your service is using your another service, then you can use service accounts, which are managed by Kubernetes API, and credentials are stored as Kubernetes secrets. One of the primary user types in Kubernetes is a service account. Service account exists in and is managed by the Kubernetes API. The credentials for service accounts are stored as Kubernetes secrets, which allows them to be used by authorized pods to communicate with the API server. Most API requests provide an authentication token for service accounts or a normal user account. As I said, normal user accounts allow more traditional access for human administrators or developers, not just services and processes. Kubernetes itself does not provide an identity management solution where regular accounts and passwords are stored. Instead, external identity solutions can be integrated into Kubernetes. For AKS cluster, this integrated identity solution is Azure Active Directory. So as you see, for access and identity, you have two types of accounts, and you can manage easily with those two types of account. I hope it's clear. So Next is Azure Active Directory integration into Kubernetes. You can use Azure Active Directory as an integrated identity solution. As I said, this is for user accounts. The security of AKS cluster can be enhanced with the integration of Azure Active Directory. Built on decades of enterprise identity management, Azure AD is a multi-tenant cloud-based directory and identity management service that combines core directory services, application access management, and identity protection. With Azure AD, you can integrate on-premises identity into AKS cluster to provide a single source for account management and security. We will talk about Azure Active Directory later on, but main advantage of Azure Active Directory is easy to manage and single identity all over the organization. With Azure Active Directory integrated AKS cluster, you can grant users or groups access to Kubernetes resources within a namespace or across the cluster. To obtain a kubectl configuration context, a user can run the AZ-AKS get credential command. When a user then interacts with the AKS cluster with kubectl, they are prompted to sign in with their Azure Active Directory account. This approach provides a single source for user management and password credentials. The user can only access the resources as defined by cluster administrator. So here, when a user tries to access the cluster, it redirects to Azure Active Directory and credentials get verified, and Azure Active Directory issue a token, and then it is validated, and for the next time it can directly access the nodes. We will talk about it when we do a real lab where you will see where you will use many Azure CLI commands. So AKS get credential command will be also used there. Next is role-based access control. So the first one was what? Azure AD integration, that is for user accounts. Next is role-based access control. So assign users or group permissions to manage Kubernetes. These permissions include create or modify resources, view logs, deploy application workloads. Permissions can be scoped to a single namespace or the entire AKS cluster. And permissions can be encapsulated in role-based access role definitions to provide granular filtering of the actions that users can perform. Kubernetes uses role-based access control. This control mechanism lets you assign users or groups of users permissions to do things like create, modify resources, view logs, as I already said, running application workloads. These permissions can be scoped to single namespace, can be granted across the entire AKS cluster. With Kubernetes role-based access control, you can create roles to define permissions and then assign those roles to users with role bindings. Azure role-based access control, one of the additional mechanisms for controlling access to resources is Azure RBAC. Kubernetes RBAC is designed to work on resources within your AKS cluster. The Azure RBAC is designed to work on resources within your Azure subscription. With Azure RBAC, you create role definition that outlines the permissions to be applied. A user or group is then assigned this role definition for particular scope, which could be an individual resource, a resource group, or across subscription. So in AKS you have RBAC. In Azure also you have RBAC. You create a role-based role in Azure RBAC, and you can apply that role into Kubernetes. So after all these type of authentications and authorizations, we have security, which is more important. And you in Kubernetes you have different type of level of security: master security, node security, and cluster upgrades. So master security, Kubernetes includes security components such as network policies and secrets. Azure then adds in components such as network security groups and orchestrated cluster upgrades. Case, the Kubernetes master components are part of the managed service provided by Microsoft. Each AKS cluster has its own single-tenanted dedicated Kubernetes master to provide the API server, scheduler, and other items. This master is managed and maintained by Microsoft. Then you have node security. AKS nodes. AKS nodes automatically deployed with the latest solution. Um, Latest OS security updates and configuration. AKS nodes are Azure virtual machines that you manage and maintain. The nodes run an optimized Ubuntu Linux distribution with the Docker container runtime. When AKS cluster is created or scaled up, the nodes are automatically deployed with the latest OS security updates and configurations. The Azure platform automatically applies OS security patches to the nodes on a nightly basis. If an OS security update requires a host reboot, that reboot is not automatically performed. And then there is a cluster upgrade. For security and compliance, or to use the latest features, Azure provides tools to orchestrate the upgrade of an AKS cluster and components. This upgrade orchestration includes both the Kubernetes master and agent components. You can view a list of available Kubernetes versions for your AKS cluster. To start the upgrade process, you specify one of these available versions. Azure then safely cordons and drains each AKS nodes AKS node and perform the upgrade. Then we go to network security. Network security groups, NSG, which you have in Azure for every resource. Kubernetes includes security components such as network policies and secrets. Azure then adds in components such as NSG and orchestrated cluster upgrades. These security components are combined to keep your AKS cluster running the latest OS security updates and Kubernetes releases, and with secure port traffic and access to sensitive credentials. Network security groups you already know or not. If not, then to filter the flow of traffic in virtual networks, Azure uses NSG rules. These rules define the source and destination IP ranges, ports, and protocols that are allowed or denied access to resources. Default rules are created to allow TLS traffic to Kubernetes API server and for SSH access to the nodes. As you create services with load balancer, port mappings, or ingress routes, AKS automatically modifies the network security group for traffic to flow appropriately. So network security groups play a big role in AKS security, Kubernetes security. Then there comes networking. Kubernetes provides abstraction layer on top of Azure networking to allow access to your applications or for application components to communicate with each other. Kubernetes provide an abstraction layer to virtual networking. Kubernetes nodes are connected to a virtual network and can provide inbound and outbound connectivity for pods. The kubeproxy component runs on each node to provide these network features. In Kubernetes, service logically group pods to allow for direct access via an IP address or DNS name and on a specific port. You can also distribute traffic by using a load balancer. More complex routing of application traffic can also be achieved with ingress controllers. Security and filtering of the network traffic for pods is possible with Kubernetes network policies. The Azure platform also helps to simplify virtual networking for AKS clusters. When you create a Kubernetes load balancer, the underlying Azure load balancer resource is created and configured. As you open network ports to pods, the corresponding Azure Network Security Group rules are for configured, and for HTTP application routing, Azure can also configure external DNS as new ingress routes are configured. So networking is also really important in AKS as in every other service, but here you have different type of network, different type of possibilities to handle the security and communication between your applications component and your applications. Next is networking connectivity. To simplify the network configuration for your application workloads, Kubernetes uses services to logically group a set of pods together and provide network connectivity. The services types are available are cluster IP and node port. Cluster IP creates an internal IP address for use within AKS cluster, good for internal only applications that supports other workload within the cluster. Node port creates a port mapping on underlying node that allows the application to be accessed directly with the node IP address and port. So internal traffic can be handled with cluster IP and external traffic is handled by node port. So you have incoming traffic which is on port same port AKS nodes, and then node port distributes this with in cluster IP. A pod is wrapper for one or more containers. All containers in the same pod share resources and networking components to facilitate easy communication as if they were on the same machine. Another factor in network connectivity are load balancer and external name. To simplify the network configuration for application workloads, Kubernetes uses services to logically group a set of pods together and provide network connectivity. The following service types are load balancer and external name. Load balancer creates an Azure load balancer resource, configures an external IP address, and connects the requested pods to the load balancer backend pool. to allow customers traffic to reach the application. Load balancing rules are created on the desired ports. External name creates a specific DNS entry for Azure application access to have your custom names. Next is storage. 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 Local storage on the Node.js on the node is fast and simple to use. Applications that run in Azure Kubernetes Service may need to store and retrieve data for some application workloads. This data storage can use local fast storage on the node that is no longer needed when the pods are deleted. Other application workloads might require storage that persists on more regular data volumes within the Azure platform. Multiple pods might need to share the same data volume or reattach data volumes if the pod is rescheduled on a different node. Finally, you might need to inject sensitive data or application configuration information into pods. Persistent storage volumes. Volumes are defined and created as part of the pod lifecycle and only exist until the pod is deleted. Pods often expect their storage to remain if a pod is rescheduled on a different host during a maintenance event, especially in stateful sets. A persistent volume is storage resource created and managed by Kubernetes API that can exist beyond the lifetime of an individual pod. Azure disks or files are used to provide the persistent volume. As noted in the previous section on volumes, the choice of disks or files is often determined by the need for concurrent access to the data or the performance tier. So storage exists beyond the lifetime of the pod. Storage can be a service such as Azure Files or an Azure managed disk. Scaling. Applications might grow beyond the capacity of a single pod. As you run applications in AKS, you might need to increase or decrease the amount of compute resources. As the number of applications instances you need to change, the number of underlying Kubernetes nodes might also need to change. You also might need to quickly provision a large number of additional application instances. So there are two types of auto scaling: horizontal pod autoscaler, which is this one, and cluster autoscaler. Horizontal pod autoscaler. Cluster uses horizontal pod autoscaler to monitor the resource demand and automatically scale the number of replicas. By default, the horizontal pod autoscaler checks metrics API every 30 seconds for any required changes in replica count. When changes are required, the number of replicas in the increased or decreased number of replicas is increased or decreased accordingly. So every 30 seconds, it checks if they need to auto scale. Then there is cluster autoscaler. To respond to changing pod demands, Kubernetes has cluster autoscaler that adjusts the number of nodes based on the requested compute resource in the node pool. By default, the cluster autoscaler checks the API every 10 seconds for any required changes in the node count. If cluster autoscale determines that a change is required, the number of nodes in your AKS cluster is increased or decreased accordingly. So everything is automatically managed. Horizontal pod autoscaler is checked every time, 30 seconds, and cluster autoscaler checks every 10 seconds. Scalar Scaling to Azure Container Instances. Burst container instances. To rapidly scale your AKS cluster, you can integrate with Azure Container Instances. Kubernetes has built-in components to scale the replica and node count. However, if your application needs to scale rapidly, a horizontal pod autoscaler may schedule more pods than can be provided by the existing compute resources in the node pool. If configured, the scenario would then trigger the cluster autoscaler to deploy additional nodes in the node pool, but it might take a few minutes for those nodes to successfully provision and allow the Kubernetes scheduler to run pods on them. If you need to rapidly grow your AKS cluster, you can create new pods in Azure Container Instance. So you see, you can easily create um, new instances in your Azure AKS and AKS cluster. Rapid burst scaling. Now we are going to the lesson 2, deploy an AKS cluster. In this lesson, you will cover deploying to AKS using Azure CLI, deploying applications to AKS, deploying an AKS cluster by using Azure Portal. Deploying to AKS by using Azure CLI. For every resource, what you need to create a resource group. So first we create AZ resource group, and then we create AKS cluster. Create a resource group with AZ group create command. An Azure resource group is logical group in which Azure resources are deployed and managed. When you create a resource group, you are asked to specify location. This location is where your resources run in Azure. And then you simply create a cluster. Use AZ AKS create resource group my group, and then name of the cluster, then node count, and then enable add-ons monitoring, generate SSH keys. Simple. AZ AKS create command to create AKS cluster. This example creates a cluster with one node and enables features such as container health monitoring by using enable add-ons monitoring parameter. And then you need to connect the CTL client to AKS. So for that you need to install AKS in your CLI. To manage Kubernetes cluster, we use kubectl, the Kubernetes command line client. Note, if you are using Azure Cloud Shell, kubectl is already installed. If you want to install it locally, then you have to install it using AZ-AKS install CLI command. Then we need to get the credentials from for this cluster we just created, and then we get list of cluster nodes in this cluster. kubectl get nodes, sorry, cluster nodes, total number of list of nodes. The AZ-AKS get credential command downloads credentials and configures the Kubernetes CLI to use them. So then you don't need to send every time the credentials. Once you get AZ-AKS get credentials, and for the next commands to verify the connection to your cluster, then you use kubectl get command to return list of cluster nodes. It can take few minutes for the nodes to appear. Then you have a Kubernetes manifest. A Kubernetes manifest file defines a desired state for the cluster, including what container images should be running. This YAML file describes a deployment that runs the nginx 1.7.9 Docker image, and in this one you have uh, metadata nginx deployment, and then you're specifying the app is nginx and the image is nginx 1.7.9 and container port is 80. Then if deploying application to AKS, to verify the connection to your cluster, then you use kubectl get command with the nodes noun to return a list of cluster nodes. It can take a few minutes as before to appear. Then you use kubectl apply command to run the application described in the manifest example.yaml file. The application is run. As the application is run, a Kubernetes service is created that exposes the application front end to the internet. This process can take few minutes to complete. Then you run kubectl get service with the noun service command to monitor the progress of the deployment, which we called the nginx deployment recently, which we did here, nginx deployment in our YAML file. In this YAML file, we called it nginx deployment. So we are saying simply kubectl get service, which we just had in this YAML file, and then we watch it, and we just run the application using example.yaml, which is this one, and now we watch the status. And finally we use kubectl get pods noun with the noun pods to view the list of pods related to your deployment. So you say l app equals to nginx. You simply filter with app equals to nginx because we just said app here is nginx. So I hope it's clear. Now deploying an AKS cluster by using Azure portal. You can use Azure portal to create and configure an AKS cluster in a manner similar to using any other tool, PowerShell, CLI, or SDKs. You can examine the same configuration options from the CLI in the portal interface. Let me show you in my app. Create a resource. I'm just going to create a Kubernetes cluster. Here it is asking me about my subscription, and then I want to create a new resource group, which is AZ-203 AKS. Okay, and cluster name. So I need to specify my cluster name. AZ-203 my cluster. My region is by default taken, which is West Europe. Kubernetes version is 1.14.8, which is default version. I can change, I can go to other versions. and there are preview versions as well, but I don't want to use previews. And it is default, by default it is having DNS prefix with my DNS. So DNS name prefix used with the hosted Kubernetes API server. You will use this to connect to Kubernetes API when managing container after creating the cluster. So as I said already, you can have your own DNS, and this will be used later on to access your API, access your cluster. The primary node pool. The number of size of nodes in the primary node pool in your cluster. For production workloads, at least 3 nodes are recommended for resiliency. For development or test, only 1 node is required. You will not be able to change the node size after the cluster creation. So you have to pay attention to this. You have to specify the node size and you have to determine it in advance. But you will be able to change the number of nodes in your cluster after creation. If you would like to additional node pools, you will need to enable the X features on Scale tab, which will allow you to add more node pools after creating the cluster. So node size is standard DS2v2. Okay, node count is 3, and I don't need 3. Okay, but I will leave it. Next is scaling. Here in the scaling, virtual nodes disabled, VM scale set enabled. Because what is VM scale set? Because nodes are simply virtual machines, or type of you can say they are type of virtual machines. So what we want to auto scale these nodes when you have load, which we just discussed, cluster auto scaling and horizontal auto scaling. So for that we need auto scaling, for VM auto scaling. I said okay. And next I go to authentication. As I said, I can have cluster infrastructure with service principal, and I can enable a role-based authentication. So service principal is I can simply configure service principal. I can create a new service principal, create new or use existing if I have any, if I've created any, or I can create new. So but I am not going to create one. And I want to use RBAC. Next, networking, which we just talked about. Private cluster networking, HTTP application routing, load balancer, network configuration. These 4 type of networking we just talked about. And here you can enable and disable them. If I enable it, it will automatically configure for me. A private cluster uses an internal IP address to ensure that network traffic between the API server and node pools remain on a private network only. But by default it is disabled. HTTP application routing. This solution makes it easy to access applications that are deployed on your cluster by creating publicly accessible DNS names for application endpoints. This will create a DNS zone in your subscription. HTTP application routing is designed for easily getting started with ingress controllers and such is not recommended for production cluster. And load balancer is standard, which has expanded capabilities compared to the basic SKU. It is used for all cluster created in Azure portal. If you need to create your Kubernetes cluster with a basic load balancer instead, for example, if your organization prohibits public IP addresses or on Kubernetes cluster, then you will need to create your cluster using the CLI or an alternate method, but you cannot change the load balancer on Azure portal. So they gave you default load balancer and you cannot change it. Network configuration, which is basic, you can change it. Kubenet with the default VNet or advanced configuration using Azure CNI with option to customize your VNet. So you can go with advanced, but then you are going to define all the rules, DNS, Docker bridge address, cluster subnet, everything. I go with basic because yeah, this is not something you need to worry about. Let's say when you going with default storage options, storage account, then it might be a problem because Azure gives you default options which are expensive, but sometimes for networking you should depends if you really need to specify, then you can change it or you can otherwise I would go with the default versions because those are uh, suggested and are not expensive, or you don't pay for that as well. Actually, enable container monitoring and log analytics workspace. So this is automatically created. I'm not going to create any tag. So let's create this, just running the final validation, and then I should have a okay, and now I can create my Kubernetes cluster. Okay, the deployment is underway. It's interesting to see what type of resources it creates for AKS. You see workspace deployment, Microsoft that resource deployment. So first it creates the deployment, and it created the deployment. Now it is creating managed clusters, which is, so if you see it just deployment succeeded. Let's go to the resource. Deployment succeeded. I just here you have your resource group, the location we chose, and subscription. As we have no tags, and Kubernetes version is 1.14.8 with our API server address, which was automatically created, AZ-203 my cluster, then DNS, and then it adds automatically some default value here to make it unique, and then .hcp.westeurope.azmk8s.io. This is a real address, and this you can use for your API. And then if we go for the node pool, we have no node, one node pool, sorry, with Linux version with 3 node count and node size. This is the one we created. So if you see our Azure cluster is Kubernetes services is up and running. And if we go to upgrade, we can change the current version. Scaling. Scaling is by default 3. Since the cluster support multiple node pools, you will need to scale your cluster node pools individually by going to the node pools resource menu item. You cannot directly scale from here. For networking, we chose the default networking, so basic kubenet. So we have with this Docker bridge IP address, we can directly access it. So that's it about creating a Azure AKS cluster using a portal. We just did it using Azure portal. And the next is publish a container image to container registry. So in this lesson, we will learn Azure Container Registry, Azure Container Registry build, deploy an image to container registry using Azure CLI. So Azure Kubernetes Services is simple orchestrator with nodes we created. Now we need Azure Container Registry ACR for the images, and we deploy an image to that container registry using Azure CLI. Let's go. So here, create a Azure Container Registry. Azure Container Registry is a Docker registry service based on open source Docker Registry 2.0. Create and maintain Azure Container Registries to store and manage your private Docker container images. You use container registries in Azure with your existing container development and deployment policies. Use Azure Container Registry build ACR build to build container images in Azure, build on demand or fully automate builds with source code commit and base image update build triggers. So you can also include it in your CI/CD pipeline and build trigger builds and publish using that pipeline. So simply Azure Container Registry is the one which contains Docker container images. Tight integration with multiple Azure services that supports the Docker images such as Azure App Service, Azure Batch, Azure Service Fabric, and then Azure Container Services. In this, key terminologies are registry, repository, image, and container. You need to understand one by one every one of them. So registry, create one or more container registries in your Azure subscription. Registries are available in 3 SKUs: basic, standard, and premium, each of which support webhook integration. Registry authentication with Azure Active Directory and delete functionality. Take advantage of local network close storage of your container images by creating a registry in the same Azure location as your deployments. Use the geo-replication feature of premium registries for advanced replication and container image distribution scenarios. A fully qualified registry name has the form myregistry.azurecr.io. You control access to container registry using an Azure Active Directory packed service principal or provided admin account. Run the standard Azure Docker login command to authenticate with a registry. So you create a registry and you can authenticate yourself using Azure Active Directory backed service principal, or so Azure Active Directory backed by service principal or provided admin account that you run the standard Docker login command to authenticate with the registry. What is repository? A registry contains one or more repositories which store groups of container images. Container registry supports multi-level repository namespace. With multi-level namespace, you can group collection of images related to a specific app or a collection of apps to specific development or operational teams. For example, you have my registry Azure CR.io. Then you say ASP.NET Core, which is the name of repository, then you say 1.0.1, which represents a corporate wide image. Then you say with the same DNS, you say warranty depth.net build represents an image used to build .NET apps shared across the warranty department. So you can simply divide using the repositories. You can say you can use the warranty department, then customer submissions, then web. That means like you can simply go in structure where you can divide repositories and access those repositories based on the names. Then you have image stored in a repository. Each image is a read-only snapshot of Docker-compatible container. Azure Container Registries can include both Windows and Linux images. You control image names for all your container deployments. Use standard Docker commands to push images into repository or pull an image from repository. In addition to container images, Container Registry stores related content formats such as Helm charts used to deploy applications to Kubernetes. So a registry contains repository contains images, simple. And a container defines a software application and its dependencies wrapped in a complete file system including code, runtime, system tools, and libraries. Run Docker containers are based on Windows or Linux images that you pull from Container Registry. Containers running on a single machine share the operating system kernel. Docker containers are fully portable to all major Linux distros, Mac OS, and Windows. So simply a container defines a software application and its dependencies wrapped in a complete file system including code, runtime, system tools, and libraries. So I hope it's clear, but I would like you to go again these definitions and understand them in a better way. Now, Docker containers and registries. Registry has repository which is getting a container image from Docker host. Let's examine how container repositories function in the Docker ecosystem. In Docker ecosystem, a container registry contains a set of container repositories. Container repositories functions like code source control repositories as they store versioned copy of a container image. A machine running Docker can pull a container image from a registry and create a new container instance from the image. So simply a registry contains multiple repositories, a repository contains multiple versioned containers, and now I hope it's more clear. So container registry SKUs. A container registry is available in different SKUs that provide predictable pricing and options for aligning to capacity and usage patterns of a private Docker registry in Azure. You have basic, standard, and premium. Basic, a cost-optimized entry point for developers learning about container registries. Basic registries have the same programmatic capabilities as standard and premium. Azure Active Directory authentication, integration, image deletion, and webhooks. However, there are size and usage constraints. So you cannot use it for production. Standard. The standard registry offers the same capabilities as basic, but increased storage limits and image throughput. Standard registries should satisfy the needs of most production scenarios. Generally, you use standard for the production, but then there is also premium registry have higher limits on constraints such as storage and concurrent operations, including enhanced storage capabilities to store high volume scenarios in addition to higher image throughput capacity. Premium adds features like geo-replication for managing a single registry across multiple regions, maintaining a network close registry to each deployment. So I hope it's clear with the container registry SKUs. Next is create a container registry by using Azure CLI. So now we need to create a registry using CLI. What we have Azure ACR, which is Azure Container Registry. Create resource group, because every time we need to provide the name of the resource group where we want it, and the name of the container registry instance, and the SKU basic. And once it is created with default integration, then you can get the login for this ACR. This is you can create Azure ACR create command creates a container registry instance. The registry name must be unique within Azure and must contain 5 to 50 alphanumeric characters. When the registry is created, the output is like admin user enabled, creation date, ID, location, login server, name of the container registry, provisioning state, resource group, and it talks about SKU, status, storage account. Before pushing and pulling container images, you must log into container registry instance. To do so, you do Azure ACR login with the name of the ACR container registry name, and the command returns login succeeded message after it is completed. And then you can do all the other operations in addition to container registry. And build a Docker image for container registry. Now we created a container registry. Now we need to build a Docker image for this registry. So what we do, we pull a Docker image simply, and then we obtain the full login server name of the container registry instance, then tag the image with full login server name prefix, and then push the image to the container registry. To push an image to Azure Container Registry, you must first have an image, right? If you don't have any local container image, you can pull an existing images from Docker Hub. So this is what we are doing here. Docker pull from where? Microsoft ACI hello world. Before you can push an image to your registry, you must tag it with a fully qualified name of your container registry login server. The tag the image using the docker tag command. So we pulled the image, then obtain the full login server name of the container registry instance, and then we need to tag it. So we tagged this image, tag Microsoft ACI hello world with login server, and we tag it with version 1 v1. And in the end, then we can push it using the same tag, ACI login server / ACI hello world, and then v1. So and now we can view this Docker image from the container registry. To view a deployed image in container registry by using CLI, we use the AZ-ACR repository list with the command to list the repositories in the registry. The output should appear similar to the containing the name of the images. And then we use AZ repository show tags and with the name of the ACR name repository this and output as a table which shows the tag as we used the tag here in this one as hello world v1. So it should show the tag in with this output as v1. So the result will be v1. And now once we deploy an image to container registry. Now we need to, so just to summarize it again, what we did, we created a container registry, then we build a Docker image for container registry, then we just viewed that image in the container registry. Now we deploy an image to container registry by using CLI. To deploy a container instance from the registry you created, you must provide the registry credential when you deploy it. In production scenarios, you should use a service principal for container registry access, but in this example, we will enable the admin user on your registry. After admin is enabled, the user is the same as your registry name, and you can retrieve password by using AZ-ACR credentials show command. You can use AZ container create command to deploy your container image. In this example, we deploy a container with 1 CPU core and 1 GB of memory. So what we do, first we enable admin user, AZ-ACR update name of the Azure Container Registry, then admin, then enabled true. Then with query for the password, we deploy the container image. So we create container, Azure Container create in this resource group, in this ACR quick start with the name and image which we just created with 1 CPU, memory 1 GB, and registry username ACR name, registry password ACR password we just acquired, and then DNS name label FQDN, and then port with 80. So once we deployed it, now we can view the container FQDN, Azure Container show resource group, my ACR quick start query instance view dot state. By using this query instance view dot state, we can view the status of the deployed container image. Now we deployed the container image. After that, we can Azure Container Registry build. So we can now use the build. ACR tasks is a suite of features within container registry that provides streamlined and efficient Docker container image build in Azure. ACR build is one of the tasks available in ACR tasks. Suite of features within container registry that provides streamlined and efficient Docker container image build in Azure. Offloads Docker build operations to Azure. Replace manual build by using Docker tools on your local machine. Build on demand. And then you can fully automate builds with your source code commit and base image update build triggers. So you can use it in CI/CD. Next is building images in container registry. Let's examine how a container registry handles the build task. Azure-based container builds are executed by using the ACR build command. So you build the Azure Container Registry The AZ-ACR build command using the Azure CLI tool receives a context, the set of files to build from the local machine, sends the context to Azure Container Registry tasks, and by default pushes the built image to its repository upon completion. You will learn about the components of AZ-ACR build command next in the next slide. Here you have container registry. So Azure Container Registry build. You have a you trigger a build in Azure is using AZ-ACR build image, and then you put the server, which is registry server, Docker tag, which is the tag you just created using the Docker tag, and the registry, which is the path to build. So that the code from your local machine will be uploaded to the build server, and then the Docker file will be used in the build process. So it looks simple and small code, but this does a lot. Okay. Create and run container images in container instances. So in this lesson, we will learn Azure Container Instances, create container for deployment to container instances, deploy a container to container instance, implement an application by using virtual kubelet. Azure Container Instance ACI. So we just learned about ACR, Azure Container Registry. Now we are learning about Azure Container Instances. Containers are becoming the preferred way to package, deploy, and manage cloud applications. Container instances offer the fastest and simplest way to run a container in Azure without having to manage any virtual machines and without having to adopt a higher level service. Container instances is a good solution for any scenario that can operate in isolated containers, including simple applications, task automation, and build jobs. For scenarios where you need full container orchestration, including service discovery across multiple containers, automatic scaling, and coordinated application upgrades, then I recommend using Azure Kubernetes Services. Container can be provisioned with public IP address and DNS name. It supports direct mounting of Azure file shares. It supports Linux and Windows containers. Ideal for one of the isolated container maintenance, simple applications, task automation, and build jobs. So next is container groups. Let's examine the role of container group and container instances. So you have container group is a top level resource in container instances. A container group is collection of containers that get scheduled on the same host machine. The containers in a container group share a life cycle, resources, local network, and storage volume. This example of container group is scheduled on a single host machine, is assigned a DNS name label, expose a single public IP address with one exposed port, consists of two containers. One container listens to port 80 while the other listens to port 1433. Includes two file shares as volume mount, and each container mounts one of the share locally. So you see within a container instance, you have a container group. Then next is container features. Fast startup times. Container Containers offer significant startup benefit over virtual machines. Container instances can start containers in Azure in seconds without the need to provision and manage virtual machines. Public IP connectivity and DNS name. Container instances enable exposing your containers directly to the internet with an IP address and fully qualified domain names. When you create a container instance, you can specify a custom DNS name label. So your application is reachable at customizable.azureregion.azurecontainers.io. Then hypervisor level security. Historically, containers have offered application dependency isolation and resource governance but have not been considered sufficiently hardened for hostile multi-tenant users. Container instance guarantees your application is as isolated in a container as it would be in a virtual machine. So the isolation is still the same as virtual machine. Custom sizes. As demand for resources increases, the nodes of an AKS cluster can be scaled out to match. If resource demand drops, node can be removed by scaling in the cluster. AKS scale operation can be completed using the Azure portal or the CLI. For compute-intensive jobs such as machine learning, container instances can schedule sorry, Linux containers to use NVIDIA Tesla GPU's resources. Persistent storage. To retrieve and persist state with container instances, we offer direct mounting of Azure file shares. Sorry. Linux and Windows containers. Container instances can schedule both Windows and Linux containers with the same API. Simply specify the OS type when you create your container groups. Some features are currently restricted to Linux containers. While we work to bring feature parity to Windows containers, you can find current platform differences in quotas and region availability for container instances. So that you can make yourself familiar with the Linux and Windows containers. Container instance supports Windows image based on long-term service channel (LTSC) version, Windows semi-annual channel (SAC). Releases like 1709 and 1809 are supported. Co-schedule groups. Container instances supports scheduling of multi-container groups that share a host machine, local network storage, and life cycles. This enables you to combine your main application container with other supporting role containers such as logging sidecars. Virtual network deployments. Container instances enables deployment of your instances in Azure Virtual. They can communicate securely with the other resources in the virtual network, including those that are on premises through a VPN gateway or express route. Now let's talk about Docker terminologies. You have many Docker terminologies as container image, build, pull, push, Docker file. You should be familiar with these key terms before using Docker and container instances to create, build, and test containers. So, container. This is an instance of Docker image. It represents the execution of a single application process or service It consists of contents of a Docker image, an execution environment, and a standard set of instructions. When scaling a service, you create multiple instances of a container from the same image, or a batch job can create multiple containers from the same image, passing different parameters to each instance. Container image. This refers to a package with all the dependencies and information required to create a container. The dependencies include frameworks and the deployment and execution configuration that a container runtime uses. Usually an image derives from multiple base images that are layers stacked on top of each other to form the container file system. An image is immutable once it has been created. Then build. This refers to action of building a container image based on the information and context provided by its Docker file, plus additional files in the folder where the image is built. You can build images by using the Docker build command. Docker build. Then there is pull, which is refers to the process of downloading container image from the container registry. There is push, which refers to pushing or uploading the container image to the container registry. There is Docker file. This refers to the text file that contains instructions on how to build a Docker image. It is like a batch script. The first line states the base image, followed by the instructions to install required program, copy files, and so on until you get the working environment you need. So basically, it's a YAML file containing all the instructions to create your work environment ready. Create a container for deployment to container instances. So this is a simple example of container for deployment. The same simple application is in this tutorial is a simple web app built in Node.js. The application serves a static HTML page, and you can use Git to clone the sample applications repository, which are in Azure samples, and you can get it. I will put the URL: Azure sample ACI hello world Git. The Docker file for an application shows how the container is built. It starts from an official Node.js image based on Alpine Linux, a small distribution that is well suited for use with containers, and it then copies the application files onto container, installs dependencies by using Node Package Manager, and finally starts the application. So simply it's use from node 8.9.3 Alpine, then run, which makes directory user source app, then copy .api .app to user source pop app, then working directory changes to user source app, then run npm install, run all the dependencies, then cmd node, and it runs the set the command. Let's break it down. Build a container prior to container instances deployment. Use the docker build command to create the container image and tag it as ACI tutorial app, as we did it here. Output from this build file, build command, is similar, where you have as information about Docker build step, what steps it took, and all the steps, step by step it will show that. And in the end, we can use the Docker command to examine the built image. Your newly built image should appear in the list. So then you can say Docker images, and there your ACI tutorial app with latest tag will appear there with the test the container prior to container instance deployment. So to test your container before your deployment, your container instance is deployed. Before you deploy the container to container instances, you use Docker run to run it locally and confirm that it works. The D switch lets the container run in the background, while P allows you to map an arbitrary port on your computer to port 80 in the container. The output from the Docker run commands displays a running container's ID if the command was successful run. So then if we run this, we should have the ID of the container's ID. Then you can view all the running containers by using view docker container LSA, which shows all the running containers. Deploy a container to container instance. When you are ready that your framework works, then you can deploy a container to container instance. And when you deploy an image that hosted in a private container registry, you must supply the registry credentials. So first, get the full name of the container registry login server. So for that, you do AZ-ACR, Azure Container Registry, show name of the Azure Container Registry, and then query is login server. So you get the login server. Next, you get the container registry password. So to get the container registry password, you do AZ-ACR credentials, so name, the ACR name, and then query is password, because passwords are a set of passwords are stored in an array, so you can get them with value. So once you have registry login server and registry password, then now you can use the Azure Container Create command to deploy the container. And to do so, you do Azure Container Create in the resource group, the name of the app and image, which is we just created with the CPU 1, memory 1, and the login server. This one we just got it, and registry username, registry password, and DNS name label which we want. So simply to get you do it in 3 tasks. Deploy a container to container instance. You do it in 3 steps. First, you get the full name of the registry container registry login server. Then you get the container registry password, and then you deploy the container using Azure Container Create. To verify the deployed container in the container instance, we do Azure Container show resource group, which resource group I am in, and the name of the container instance, which is ACI tutorial app, and provisioning state. So query is provisioning state, which show me the status of the deployment. And now to view the application URL, with the simple same command, just change the query IP address .fqdn. This shows you the fqdn or the application URL. Then to view the container logs, you simple say Azure Container Logs and the resource group and name of the container. Very simple. Next is virtual kubelet. When implementing a Kubernetes application, you may wish to deploy containers to services other than your Kubernetes cluster. Virtual kubelet is an open source implementation of a kubelet that allows you to use other services to back your Kubernetes cluster as opposed in the built-in nodes. Virtual kubelet is an open source implementation of a kubelet that allows you to use other services to back your Kubernetes cluster as opposed in the built-in nodes. A virtual kubelet provides a SIM layer with a pseudo kubelet implementation, enabling you to use other services for your individual instances such as Azure Batch Container Instance, Alibaba Cloud Elastic Container Instance, AWS Fargate, Kubernetes Container Runtime Interface, Huawei Cloud Container Interface, Hashi Corporation Nomad, OpenStack June. Using virtual kubelet, let's examine this example. In this example of a Kubernetes cluster, virtual kubelet is used to allow us to back our Kubernetes cluster with services such as container instances and Azure Batch. These services then host our individual nodes on behalf of the cluster. So you see here, you have using Azure Virtual Kubelet, you can use container instances and you can use Azure Batch at the same time. Let's do it in reality. Implement an application using virtual kubelet. When using virtual kubelet provider for container instances, both Linux and Windows containers can be scheduled on a container instance as if it is a standard Kubernetes node. This configuration allows you to take advantage of both the capabilities of Kubernetes and the management value and cost-effective benefits of container instance. To do that, install virtual kubelet connector. So you install the connector first. So AKS install connector, and then you specify the resource group and the name of the cluster and the connector name, you name it whatever, and the OS type both. So you say both Linux and Windows. Simple. You have different command arguments. You just need to go through them. So which says like connector name, resource group, OS type, container instances, operating system types, allowed value both, which is Linux, Windows, default is Linux, which is not required value. Only 3 values are required: connector name and name of the managed cluster and resource group name. Other are location, service principal, used for authentication to Azure APIs, client secret, chart URL, image tag. Virtual kubelet specifications. This file is a kubelet specification file that describes the container-based application that should run using virtual kubelet. In this example, we are using Linux-based ACI Hello World container. We could opt to use Windows-based containers such as Nano Server IIS instead. So you simply see Kubernetes IO host virtual kubelet Linux. The port is 80 open. Microsoft image is Microsoft ACI Hello World. Deploying an application by using virtual kubelet. So once you get the virtual kubelet, just to validate if you have the virtual kubelet, you say virtual kubectl get nodes, which will return you the nodes. Run the application with kubectl command, create command, and then use the kubectl get pods command with O wide argument to output a list of pods with the scheduled node. Notice that Nano Server IIS pod has been scheduled on virtual kubelet virtual machine kubelet win node. So next is Helm. Deploying applications to Kubernetes. The powerful and popular container orchestration system can be complex. Setting up a single application can involve creating multiple interdependent Kubernetes resources such as pods, services, deployments, and replicas, each requiring you to write detailed YAML manifest file. Helm is a package manager for Kubernetes that allows developers and operators to more easily package, configure, and deploy applications and services onto Kubernetes cluster. Helm is an official Kubernetes project and is part of Cloud Native Computing Federation, a non-profit that supports open source projects in and around Kubernetes ecosystem. So to use Helm, we need to initialize Helm. We use Helm init. You can initialize Helm on your Kubernetes cluster by installing a tiller. To deploy a tiller into Kubernetes cluster, use Helm init command. This command installs a tiller if it's not already installed and makes sure the version of the Helm CLI and the tiller match. Then you can deploy a Helm chart using Helm install command. The tiller will manage the deployment within the Kubernetes cluster. So you can simply use a Helm to manage all the install all your dependencies. This is an example with a few files omitted of Helm chart that runs a single pod running Alpine Linux. The chart.yaml file contains metadata about the Helm chart that is used to describe the chart. The values.yaml file defines the default values that are set but can be overridden when the chart is installed. The Alpine pod YAML file defines actual deployment to the pod, which will deploy Alpine latest image from Docker Hub. So you have three YAML files which describes and which are used for different functions. Deploying compute workloads by using images and containers. This lab we will do in a separate video because it contains a lot of work to do. These are the labs provided by Microsoft. You can find them online. If you want to do them with me, I'll do them in another video. You can find them in this Azure AZ-203 playlist, or you can do them yourself. To review this, what we did Azure Kubernetes Services, deploy an AKS cluster, publish container image to Azure Container Registry, create and run container images in Azure Container Instance, and we did not do the lab. So thank you. I hope you liked it. Please ask your questions in the comment section below and like, share, and subscribe. Please stay tuned to watch other videos for certification AZ-203 or AZ-204. Thank you. See you. Bye.